So for this lecture, we'll be talking about arc length. So length of a given curve, okay, or a given arc. So our problem is the following. Suppose we have a function y equals f of x, and this function is a smooth curve, okay, or gives a smooth curve on the interval AB. Okay, so our goal is to define and find a formula for the arc length of the curve over the interval a b. Okay, so in here I am introducing the word smooth. Okay, when we say smooth, um, graphically you can think of this as some curve in the space that does not have any cusp or pointed part. For example, pointed part, it means something like this. So if you look at this point, this is a pointed part. Okay? So intuitively, you can think of a function which is not smooth if you can find this pointed part. Okay? Or you can think of this as something that has continuous derivatives. Okay, so if you look at the function y equals f of x, if you get the derivative of that and it is continuous, okay, then your function is smooth. Okay, in fact, it must be infinitely differentiable, meaning you can get the first derivative, it's continuous, you can get the second derivative is still continuous, etc., etc. Okay, so that's what we call smooth functions. Okay, but again, as I have said, intuitively, um, you cannot find something like this, pointed or a cusp, okay, part of the graph of the function. So that's what smooth means for us. Okay, so again, suppose we are given a curve, okay, y equals f of x, maybe the curve will look something like this. Okay, that's not smooth. So maybe the curve looks something like this. Our goal is, how do we find the length of this curve in here? So how long is this curve here when stretched as a straight line? Okay, so in order to do this, let us consider first a line segment. Okay, so if we are given 2 points, say P1 here with coordinates x1 comma y1, and then another point here x2 comma y2, say P2. Okay, and then you want to find the distance of these 2 points. What you are looking for is actually the length of the line segment. Okay, the length of the line segment joining these 2 points, x1, y1, x2, y2. And you know that the distance formula is given by this formula here. L equals square root of x1 minus x2 squared plus y1 minus y2 squared. Okay? And if you can think, or if you will think of x1 minus x2 as delta x, and then this guy here, y1 minus y2 as delta y, then the L, this is just square root of delta x squared plus delta y squared. Okay? So this is for straight line, okay? Or a line segment joined by 2 points. So the problem is, how do we use that, or can we actually use that formula in order to find the length of this curve in here? Okay? So suppose that y equals f of x is a smooth curve on the interval AB. We define and find formula for the arc length L of this curve over the interval AB. So let us draw again a smooth curve. And this time I'll just draw a shorter curve, smooth curve. say something like this. Okay. And of course, this is your interval AB, maybe. Okay. So you have the x coordinates, the y coordinates, okay, or the x-axis, the y-axis. Your A is somewhere here, your B is somewhere here, okay. So this point here, this is the point B comma F of B, okay. And this point here, this is the point A comma F of A, okay. And of course, like I said, this is your y equals F of X. So like before, in order to find the arc length of this L, we will use the same method as in finding the area of the region under the curve, or area between two curves, okay, or the volume, okay. And they were all derived using the same method as in the one we use in defining the definite integral, okay. So I hope you remember these methods. So what we do is to divide the interval, okay, AB into n subintervals. And just like before, we can think of these subintervals to have equal length, okay? So we have here x1, x2, etc. Then at some point, you have xi minus 1, and then xi here, okay? Let me write it something like this. So you have um, xi there, and then you have you have xi is minus 1, and then you have xi, okay? So let me just write it here, xi minus 1, and then this is your xi. And then you continue, etc., until you reach your x sub n, okay? And your x sub n, that is your b. And as usual, your A, it will be named as x sub 0. So the labeling will be the same. You have A less than x sub 1 less than x sub 2 until you have less than x sub n. This is the B, okay? A, it's your x sub 0, and such that x sub I minus x sub I minus 1, this is your delta x. Sorry, this is the delta x, and for all I, and this is equal to b minus a over n. Okay? Then, what we're going to do is, since we have these x coordinates here, you have the x coordinates here, okay? What we're going to do is to evaluate each of them, okay? So for example, at x sub 1, you got this point here. At x sub 2, you got this point here, etc. And then at x sub I, you got this point here. And this is your point x sub I. Sorry, this point here is your x sub I minus 1. This point here, it's your x sub I. Okay? And then, of course, you have your B at this point. Okay? Well, this is the point where B is evaluated. And of course, before that, this is your point x sub n minus 1, okay? X sub n minus 1, comma, f of x sub n minus 1, okay? And then for each, or for every consecutive pair of points that we see in here, okay? We will connect them by a line segment, okay? So we will connect them by a line segment. So for example, you got this line segment here. Okay, I hope you can see that, but you got this line segment here. You got this line segment in here. So I just draw some line segment on this part. Okay. And then on this part, you have this line segment. Okay. Etc. And then on this part here, we'll also have line segment. Okay. So in here, we will consider. So consider the line segment. Line segment joining the points. The points, you have x sub I minus 1 comma f of x sub I minus 1. Okay. And the other point is x sub I comma f of x sub I. Okay. By the distance formula, so by the distance formula, we have the length of this line segment. Okay. So L sub I, okay, this is the ith line segment. All right. So this is the ith line segment. This will be equal to the square root of x sub I minus 1 comma x sub I squared plus f of x sub I minus 1, y comma. It should be minus. And I'll write it this way. X sub I minus x sub I minus 1. It's the same. And then in here, you have f of x sub I minus f of x sub I minus 1, quantity squared. Okay? So this is just based on the distance formula from here. You got 2 points. You can write the distance, or you can get the length of this line segment joining these 2 points using this distance formula. So we just used that here. Okay? And now, look, your x sub 1, x sub 2 until x sub n, all of them are different. They are not equal. Therefore, this guy here, this guy here, x sub I, okay, x sub I minus x sub I minus 1 squared, it's not equal to 0. Okay? So what we're going to do is to factor x sub I minus x sub I minus 1 squared. So this guy in here, okay? So we are going to factor that. We will have square root of x sub I minus x sub I minus 1 quantity squared times. We have 1 minus, or 1 plus. Okay? We have 1 plus. We still have this f of x sub I minus f of x sub I minus 1 squared. Okay? And we will have denominator for that after factoring the x sub I minus x sub I minus 1. Okay? So here you have f of x sub I minus f of x sub I minus 1 divided by x sub I minus x sub I minus 1. Okay? And of course, this is enclosed inside parentheses, and we are squaring that. And now we enclose this by square bracket. So again, what did we do? We just factored out this guy here. Okay? So we factored out this guy here. And therefore, if you factor that out, in this part, you'll just have this one. While on this part, it will become this guy here. Okay? And then from here, you have square root of something squared here times this guy here. So we can bring out this x sub I minus x sub I minus 1 squared. Okay? We can bring it out outside the square root. And if we do that, we will have x sub I minus x sub I minus 1 without the square, because we have the square on this part, but we have the square root. So this guy here won't have any square. And then what remains inside, we still have that 1 plus quantity f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. And then quantity here, we square that. Okay? Following so far? Okay? Now, of course, this guy here, this is just your delta x. Okay? This is just your delta x. So we can replace that by delta x. Okay? By the way, more formally, this guy here, this is delta x sub I because we are talking about the ith interval here. Okay? But anyway, since we have divided it into n subintervals of equal length, you can remove the subscript in here. Okay? Now, in fact, in this computation here, okay, in this computation here, in our derivation, we don't even need to divide the whole interval into subintervals of equal length. We really don't care about that one. In the um, computation or the derivation of the formula that we will get. But anyway, so it won't hurt us anyway if we do this equal subdivision. Okay? Now, this guy here will be replaced by delta x sub I. But remember when we are doing definite integrals, okay? When we are doing definite integrals, you have, say, integral from a to b of some function g of x dx. This is equal to the limit n goes to infinity, summation I from 1 up to infinity of g of x sub I star delta x sub I. In this part, okay, from this part here, we will need some x sub I star. We will choose it properly, okay? In the previous derivation, in the previous, like the derivation of area between curves, as well as the derivation of the volume of the solid of revolutions, using the method of washers and method of this, we can choose any x sub I star. We can choose it everywhere. When we discussed volumes using the method of cylindrical shells, okay, we specifically chose x sub I star to be the midpoint of the interval. Okay? In this derivation, okay, in the derivation here, we will also choose specifically what x sub I star is. Okay? And here's how we're gonna choose it. Okay? Take note that the function y equals f of x, it is smooth on the interval AB. It means it is differentiable on the interval AB, and furthermore, it is continuous. I mean, the derivative is continuous. Okay? So the function y equals f of x is differentiable on the interval AB, and furthermore, um, the derivative is also continuous. Okay? We don't need the continuity of the derivative, however, in choosing this guy here. Okay? In choosing the x sub I star uh, for this function or for this formula here. Okay? So how are we gonna choose the x sub I star? Since f or y equals f of x is smooth, since y equals f of x is smooth on AB, okay, f is differentiable, okay, differentiable on AB, okay, and furthermore, and in fact, differentiable on the open interval AB, okay, and so is differentiable on the ith subinterval. On the ith subinterval x sub I minus 1, comma, x sub I. Okay? And again, since we are talking about differentiability on intervals, let's put this open here. Okay? So we have a function. We have a function, f, which is differentiable on this interval, x sub I minus 1, comma, x sub I. Okay? Also, it is continuous. Also, it is continuous. Okay? Continuous on the closed interval, x sub I minus 1, comma, x sub I. Okay? Following? So from here, we will use mean value theorem. By mean value theorem, okay? By mean value theorem, there exists, here we will write it as x sub I star. Okay? There exists x sub I star inside the interval x sub I minus 1, comma, x sub I. Okay? So there exists x sub I star inside the interval x sub I minus 1, comma, x sub I, such that, what's the conclusion for the mean value theorem? This is not the mean value theorem for integrals. I'm just applying the mean value theorem, the one that you've learned from your calculus 1. Okay? So the conclusion here is there exists x sub I star inside the interval x sub I minus 1, comma, x sub I, such that the derivative of the function f at that x sub I star, okay, this is equal to the distance between the 2 points at x sub I, okay? Not really the distance. It's the ratio. This ratio here, f of x sub I minus f of x sub I minus 1 divided by x sub I minus x sub I minus 1. So it's not the distance, it's this quotient difference. Okay? This is the mean value theorem applied to this interval and this function. But look at this part here. It's precisely this guy here. Okay? So what does this mean? So L sub I, this is square root of 1 plus f prime of x sub I star, okay, times delta x sub I. This guy here, by the way, it should be squared. So L sub I, this is equal to square root of 1 plus f prime of x sub I star squared. You take the square root of that, okay? And then you multiply delta x sub I. So this guy here, we just replaced it by f prime of x sub I star. Okay? Okay? Now look, this guy here, this is just in terms of x sub I star. There are no other variables. This guy here. And since our function is smooth, like I said, it is, the derivative is also continuous. This guy here, okay, if we collect if we get the Riemann sum with this L sub i's, okay, we can convert it easily to definite integral. Okay? So, the Riemann sum, let us write it here, summation I from 1 up to n, L sub I. This is just summation I from 1 up to n, square root of 1 plus f prime of x sub I star, quantity squared, delta x sub I. So this Riemann sum approximates the length, okay? Approximates the length, of the curve y equals f of x on the interval AB, on the interval AB. It's just an approximation because again, this guy here, this is just a straight line. This guy here, it's a straight line. This guy here is also a straight line. But the curve, it's not straight. Okay? There are some concavities there. Concave up, concave down, etc. So the sum of these arc lengths here, it will only approximate. Okay? It will only approximate the arc length of this curve here. And therefore, if we let n approach infinity, if we increase the subdivision, okay, it will better approximate the length. And letting n approach infinity, okay, we will get the length of the interval, of the curve y equals f of x over the interval AB. Okay? Okay? So this is the definition of our arc length. If y equals f of x is a smooth curve on the interval AB, and then the arc length of L, okay, the arc length L of this curve over the interval AB, it's defined as this guy here. Okay? So again, coming from here, all we need to do is to take the limit as n approaches plus infinity, limit as n approaches plus infinity, and that becomes the integral. So that's how we define the length of the arc. So it's the definite integral from a to b, okay, of square root of 1 plus f prime of x squared dx. Or you can think of this f prime of x as dy over dx. Since anyway you have written it as y equals f of x. Okay? You can do the same. You can do the same derivation if you have instead x equals f of y. Derivation is um, similar. So if x equals g of y is a smooth curve on the interval CD, then the arc length L of this curve on the interval CD is defined as follows. L equals the integral from C to D of the square root of 1 plus g prime of y squared dy, or you can write it as dx over dy here. That's your g prime of y. Okay? Questions? Okay. So let's practice this formula using some of the examples I have prepared here. Use definite integral to derive the formula for the circumference of a circle of radius r. Okay? So for this, what we're going to do is to consider the following. Consider y equals, this is your f of x. Let us write this as our f of x. Square root of r squared minus x squared over the interval um, negative r comma r. So what is this? In here, you just have the semicircle. So this is your y-axis and your x-axis here. This is your r. This is negative r, and maybe let me estimate r is here. So your y equals f of x. It's just this guy here. It's the semicircle. So assume that it's a semicircle. Okay. So you have this semicircle. Y equals square root of r squared minus x squared. To get the formula of the circumference of the circle, all we need to do is to get the formula for the arc length, okay? Or, yeah, formula for the arc length of this semicircle and then multiply it by 2. So you will have the full circle. Okay? So take note, this is a semicircle of radius r. Okay? So from the center going there, it's just r. So this function, it's smooth on the interval um, negative r comma r. So just believe that this is smooth. In fact, all you need to do is to find the derivative and check that the derivatives exist. Okay? And furthermore, you have the derivative. Check if the derivative is continuous on the interval negative r to r. You have open interval, of course. So let's see. F prime of x, that's your dy over dx. dy over dx. If you calculate this is just negative x divided by square root of r squared minus x squared. So please practice your derivatives. If you get the derivative of this guy here, you'll just get this guy. Be sure to apply your chain rule. You might be wondering, sir, there should be a 2 here. But take note, if you apply chain rule, you will have negative 2x. And the 2 coming from here will cancel the 2 on the denominator. That's why you will only get this expression here. Okay? And observe that observe f prime is continuous on the interval negative r to r, open. So this function here, this is smooth. Okay, so this function here, this is smooth. In our definition, okay, in our definition. So we can find the arc length. Okay, so here f prime of x, quantity squared. So f prime of x, quantity squared, this is simply x squared over r squared minus x squared. If you square this, okay, negative x squared, that's just your x squared. You have the square root here. If you square it, it will disappear. Okay. Thus, the arc length is, so here, so the arc length is, we have L. This is the integral from negative r up to r, square root of 1 plus f prime of x squared. So this is just x squared over r squared minus x squared. Quantity squared here. Sorry, without the square anymore. And then we have the dx. Without the square anymore because we already squared it here. Okay? And let's just simplify. So we have integral from negative r up to r, square root of r squared over r squared minus x squared. And then you have the dx. Follow? Okay? And then r squared, it's just a constant. Besides, it's r squared and then you get the square root. So you'll just have integral, so equals integral from negative r up to r of r in the numerator, and then you got here on the denominator square root of r squared minus x squared dx. Okay? And then from here, we use trigonometric substitution. Okay? we use trigonometric substitution. So using trig sub, you have something squared minus x squared. So constant squared minus x squared. You have to use your sign substitution. Okay? So you let your x equals r sine theta, dx, this is equal to r cosine theta d theta. Okay? And then, of course, from here, you got square root of r squared minus x squared. You will get r cosine theta. So I hope you practiced your trigonometric substitution. Which means this guy here will just have integral from negative r up to r. Still have that r there. And then we have the r cosine theta, d theta, okay? R cosine theta d theta, that will replace the dx here. So you will have r cosine theta d theta. And then on the denominator, you'll have r cosine theta. And when you do this substitution, by the way, this is no longer r. Okay? So there will be another limits of integration in here. I'll not write it because what I'm going to do is to bring back the original um, limits of integration. But what will happen here? If we simplify everything, this will just be integral of r d theta. And then, of course, you got here and this guy here. Okay? So if we need the complete calculation for this part, let me just write it. So from here, we will have square root of r squared minus r squared sine theta. We factor out square root. We factor out r squared, so we will have square root of r squared times 1 minus, sorry, this should be squared here. So we have 1 minus sine squared theta in here. Okay? And then this guy here, let me adjust this. So this guy here will just be r squared cosine squared theta. You take the square root, and this is your r cosine theta. Okay?
Thank you.
All right. So let us continue from here. So if we do the integration, we will have equals r theta evaluated at those limits of integration. Okay? Let me move this more up there. But theta, it's just your sine inverse x over r. So this time we evaluate this from negative r up to r. So you look at this trig sub here. Okay, you look at this trig sub here. So in here, this guy here, you can have x over r equals sine theta. And that's where we will get this uh, part here. So anyway, we have here equals r, and then sine, so r times sine inverse of r over r minus sine inverse of r over negative r. Or this is equal to r times sine inverse of 1 minus sine inverse of negative 1. But sine inverse of 1, that's just pi over 2 minus sine inverse of negative 1. Remember the conditions. Remember the interval that we were using for the inverse trig function when we discussed trigonometric substitution. Okay? So this is negative pi over 2. So in the end, you will get pi r. That's the length of this semicircle here. We need the circumference of the circle. We multiply this guy here to 2. And now you see the familiar formula. Okay? All right. So the circumference is twice L, and this is twice pi r. Okay? So let me go back to these computations and try to um, analyze and internalize the solution. Okay? Let's go to our next problem. Find the arc length of the curve y equals x raised to 3 halves from the point 1, 1, comma, to the point 2, comma, 2 square root of 2. Okay? So in here, we have the point 1, 1 up to the point 2, comma, 2 square root of 2. We have the function y equals x raised to 3 halves. Okay? So if we combine this, okay? If we combine this means that our x will be from 1 up to 2. Okay? So you see, if x equals 1, then y equals 1 raised to 3 halves, which is also 1. So from here, if x equals 1, we will get y equals 1 also. And if x equals 2, using this, you will get this 2 square root of 2. So from one point on the curve, y equals x raised to 3 halves to another point on the same curve. So your interval would be from 1 up to 2. Now, y prime, what is y prime? This is just 3 halves x raised to 1 half, correct? And this one here, it's continuous. Continuous on the interval 0 to plus infinity. Therefore, your y, so y equals x raised to 3 halves this is smooth on the interval 1 comma 2. Okay, so y prime, this is your dy over dx. So dy over dx quantity squared, this is simply what? We square 3 halves x raised to 1 half, we'll get 9 over 4 x. Okay, so L, this is equal to the integral from 1 up to 2 square root of 1 plus 9 over 4 x dx. So let us just simplify this. We have the integral from 1 up to 2 square root of 4 plus 9x divided by 4 dx. Okay? Questions? So if we simplify this further, we'll just have 1 half integral from 1 up to 2 square root of 4 plus 9x. And we have the dx. Okay? So if we solve this, we let u be equal to 4 plus 9x du. This is 9 dx. If x equals 1, then u equals 13. If x equals 2, then u equals 22. Okay? So in here, we will now have, we have 1 over 9 coming from this guy here. Okay, coming from this guy here. Okay, that's 1 over 9 du. So I'll bring out that 1 over 9. And then we still have the 1 half coming from this guy here. And then we have the integral. The integral will be from 13 up to 22. Then we have square root of u. And then we have here du. So if we calculate this, this is just 1 over 18 u raised to 3 halves divided by 3 halves. Okay. Let me adjust all these calculations here. So from here, so we bring it up here. So anyway, this guy here, we will have 1 over 18 times u raised to 3 halves over 3 halves. Then here we evaluate from 13 up to 22. Okay? So we simplify this. you have 1 over 18 times 2 over 3. And then in here, you have 22 raised to 3 halves minus 13 raised to 3 halves. So you can leave the final answer in this form, or you can simplify this here. Okay, that's just 1 over 27. And then this guy here, keep it as is, this guy here. So you have 22 raised to 3 halves minus 13 raised to 3 halves. So you can have that as a final answer. Questions? Next problem. Find the exact length of the curve x equals 1/3 y squared plus 2 quantity 3 halves from y equals 0 to y equals 1. So this time you have x in terms of y, okay? X in terms of y. So we'll just use the second formula here. So this guy here, but anyway, things are the same, okay? Things are the same. So we have um, this x equals 1/3 y squared plus 2 raised to 3 halves. Let's get the derivative. So you will have your dx over dy. So it's dx over dy because you have x in terms of y. Okay? So dx over dy, this is just, so you have the 1/3. You have 3 over 2 times y squared plus 2 raised to 1 half. And then by chain rule, multiply this to 2y. Okay? So if we simplify this, we'll just end up with y times y squared plus 2 raised to 1 half. Correct? And if you look at this is continuous on the interval 0, comma 1. So this is smooth. The function, so this means that x equals 1/3 y squared plus 2 raised to 3 half. This is smooth on 0, comma y. Okay? Take note the interval here, it's the interval for y. Y equals 0 to y equals 1. Then dx over dy quantity squared. So if you square this, you will just have y squared times y squared plus 2. Or this guy will just have y to the 4th plus 2y squared. So again, we just squared this guy here. So y squared, that's your y squared here. This guy here, y squared plus 2 raised to 1 half. If you square it, 1 half will be cancelled. So this means L equals, we have the integral from 0 to 1. And then we have square root of 1 plus y squared, or y to the 4th plus 2y squared. And then you have the dy. Okay? Now look at this. This guy here, this is a perfect square trinomial. You'll just simplify this into integral from 0 to 1, square root of y squared plus 1 quantity squared. Of course, you have that dy. So if you take the square root of this square, you'll just have integral from 0 to 1 of y squared plus 1 dy. So we do the integration. This is just y cubed over 3 plus y. Then we evaluate this from 0 to 1. So this is just 1/3 plus 1 minus 0. So this is just 4 over 3. So this is the final answer. Next problem. Find the arc length of the curve y equals x to the 6 plus 8 over 16x squared from x equals 2 to x equals 3. Let us see. So y, this is x to the 6 plus 8 divided by 16x squared. Let us just simplify this. We can write this as x to the 4 over 16 plus 8 over 16. That's 2. That's 1 over 2. So 1 over 2x squared. So that's the simplified version. Or you can rewrite this as you have x to the 4 over 16 plus x raised to negative 2 over 2. And then dy over dx, this is what? 4x cubed over 16 minus 2x raised to negative 3 over 2. So if we simplify this, we'll just have x cubed over 4 minus x raised to negative 3. Okay? And then let's just square this. Dy over dx quantity squared. So you'll have x cubed over 4 minus x raised to negative 3. You square this. We'll get x to the 6 over 16 minus twice the product. So 2x cubed over 4 times x raised to negative 3, then plus x raised to negative 6. Okay? Simplifying further, well, this is just x to the 6 over 16 plus x raised to negative 6. So x raised to negative 6 and then minus 1/2. Okay? So arc length L, this is the integral from 2 to 3 square root of 1 plus x to the 6 over 16 plus x raised to negative 6 minus 1 half. Then you got here dx. Then let's just simplify this. So if we simplify this, we'll just get integral from 2 up to 3. You see there's 1 and minus 1 half. So let's just write this as x to the 6 over 16 and then plus x raised to negative 6, and then you'll get plus 1 half there, dx. Okay? And then this guy here, this is a perfect square trinomial. It's very much similar to this. Instead, we have a plus. So the one inside the square root. Okay? So you have integral from 2 to 3. The one inside the square root, what you have there is x cubed over 4 plus x raised to negative 3. Quantity squared. Then you have the dx. Okay? Which means that guy, you have the square root and you have the squared. So you'll just end up with x cubed over 4 plus x raised to negative 3. And you want to integrate this from 2 to 3 and then with respect to x. Okay? By the way, I did not mention this guy here, it's smooth. This is continuous. So this function here, the derivative function, it's continuous on the interval 0, on the interval 2, 3. Let me write that. So this guy here, continuous on the interval 2, 3. So anyway, from here, we'll integrate. So you will get x to the 4 over 4, but there's still 4 in the denominator. Then plus x raised to negative 2 over negative 2. You evaluate this from 2 to 3. Okay? Any questions? So, find the arc length of the curve 24 xy equals y to the 4th plus 48 from y equals 2 up to y equals 4. So notice how this equation is written. So if you look at this, you have a product of x and y. And then here you have y raised to power 4. And there are no other x's except from this guy here. So from here, we can easily isolate x. Okay, and we can write x in terms of y. Okay, so if we do that, we will have x equals y to the 4 plus 48, and then we divide this by 24y. Or this guy here, what do we get? We'll just have y cubed over 24 plus 2 over y. Okay? And then we have the x over dy. Since it's x in terms of y, we get the derivative of x with respect to y. This will be what? 3y squared over 24 minus 2 over y squared. And if we simplify this, we will have y squared over 8 minus 2 over y squared. Okay? And again, this is continuous on the interval 2 comma 4. So this function here, the function given by this expression here, it is smooth. Or the relation given by this expression here, it is smooth. And then next is to get the square of dx over dy. So if we square this, we'll get y to the 4 over 64 minus twice the product y squared over 8 times 2 over y squared, then plus 4 over y to the 4th. So if you simplify this, you will get y to the 4 over 64 minus 1 half plus 2 over y, 4 over y to the 4. Okay? Therefore, L equals the integral from 2 to 4 of square root of 1 plus y to the 4 over 64 minus 1 half plus 4 over y to the 4. And then you got here dy. And this will be integral from 2 to 4 square root of y to the 4 over 64 plus 1 half plus 4 over y to the 4. Very much similar to what we did in the previous example. So this will be y squared over 8 plus 2 over y squared quantity squared. So integral from 2 to the 4 square root of y squared over 8 plus 2 over y squared quantity squared, and then dy. So simplifying, you'll just have the integral from 2 to 4 of quantity y squared over 8 plus 2 over y squared dy. Okay? So you can continue the solution from here. Okay? And just give the detail on your own so you can practice. And then, yeah, that is a good practice. Okay, so thank you for noticing. This guy here, it should be from, so it should be 4. So thank you for noticing that. Okay. Questions so far? Now, there are times where a curve cannot be written explicitly as x in terms of y or y in terms of x. Okay? Sometimes the curves are written parametrically, meaning we can write x as a function of some parameter. In this case, I'll be using the parameter t. And also y is written as a function of this parameter t, meaning x equals x of t, y equals y of t. And still, your function, you can convert this into something y equals, say, f of x, okay, or y equals g of x, okay? It's just that it's easier to see, or the function is much more simpler if we write it in terms of this parameter, okay? So we call this a parametric equation. In this case, um, so we assume that no segment of the curve is traced more than once as it increases from as the t increases from a to b. Okay, meaning if you have some curve like this, it will not go back to this part. Okay, it will not go back to this part. Okay, if that happens, you should treat it separately, meaning you have to get first the interval for t until this part, and then you get the interval for t from this point up to this point. If the curve, um, if some parts of the curve is traced more than once. Okay, so we assume that our curve is just traced at most once. Okay, there is a possibility where you can have something like this. It's totally fine if the curve crosses itself. It's totally fine. We just don't want overlapping on a particular interval or on certain intervals. Of course, this curve will overlap or will intersect itself at this particular point here. It's totally fine for us because it's just a single point. Okay? We don't want overlapping curves on more than one point on consecutive, like on an interval. Okay? So if this is the case, we can still compute for the arc length. Okay? We can still compute for the arc length, and it's given by this formula. Okay? So you have the length equals the integral from a to b of square root of, take note of this, dx over dt squared plus dy over dt squared. And then the variable of integration is still t. And we are assuming that dx over dt and dy over dt are continuous functions. Okay? From a up to b. Okay? Furthermore, we don't want, okay, we don't want the case where at some point, okay, dx over dt equals 0, and up at the same time dy over dt equals 0 at some point t equals t naught. Of course, inside the interval ab. We don't want this to happen. Okay? If you are given the parametric equations, this is actually the condition of non-smoothness. Okay? So we don't want this to happen. Okay? So in here, We evaluated this at t equals 0, at t naught, at t equals t naught. We also evaluated this at t equals t naught. So we don't want this. So we don't want the derivative of x with respect to t equals 0 and the derivative of y with respect to t equals 0 at some point t equals t naught. Okay? So if at least one of them is non-zero, we say that the curve is smooth. All right? So anyway, take note from here, take note dy over dx, this is dy over dt over dx over dt. Remember your chain rule? Remember your chain rule? Okay? Your dy over dx, it's just dy over dt all over dx over dt. Okay? If you implement it here, okay, you will see that you will have the integral from a to b square root of 1 plus dy over dt over dx over dt quantity squared. And you have to factor that dx over dt, but you have the dt in here. So what happened? From here, from this guy here, we factored out this dx over dt squared. So if we factor that out, this guy here will have the denominator dx over dt, which is this part. And you factored out dx over dt squared. If we take the square root of that, you will have this dx over dt. And there's still this dt here from this guy here. So notice, we use this guy. Simplifying, you will get the integral from, take note of this, t equals a to t equals b, okay? Square root of 1 plus dy over dx quantity squared, and then you have your dx only in here. Why? Because if you notice, this dt will cancel this dt. So you'll be left with dx. But at t equals a, this means that this guy here, it's your x of a. And this guy here, this is your x of b. So chain rule. So this formula, so what I am trying to explain is this formula, it's the same formula as in before. Except that this time your curve is written parametrically. Okay? So let us use this new formula. Find the arc length of the curve x equals 1/3 t squared t cubed, y equals 1/2 t squared from t equals 0 to t equals 1. So first, let's have dx over dt. This is just t squared. Okay? dy over dt. This is just t. Okay? Now, look. Dx over dt equals 0 when t equals 0. Also, dy over dt, this is equal to 0 when t equals 0. This means the curve is not smooth. Okay? Curve is not smooth at t equals 0. But for us, it will be totally fine. Because anyway, t equals 0 is an endpoint. Take note of this. T equals 0, it's an endpoint of our interval. We can have some improper integral in here, correct? And that's just totally fine. If we have an improper integral, we can still solve it. Okay? Therefore, let's see. L, okay? This is equal to the, let's get the squares. Okay, let's get the squares first. Dx over dt squared, this is equal to t to the 4. Dy over dt squared, this is equal to t squared. Okay? So L, it's the integral from 0 to 1 of square root of dx over dt squared, that's t to the 4, plus dy over dt squared, that's t squared, and then we have the dt. And again, we can treat this as an improper integral. It's not smooth here. It's not smooth at t equals 0. T equals 0 here, it's an endpoint. We can treat this as an improper integral, but looking at it, okay, looking at it, we can also treat it as a simple definite integral, and no harm will be done. Okay? No harm will be done. So we'll just treat it as a definite integral this time. But look, let us simplify this. Integral from 0 to 1, you can factor out t squared. Here you will have t squared plus 1 dt. Or this guy here, it's just the integral from 0 to 1 of t, square root of t squared plus 1 dt. And for this one, it's just simple substitution rule. Okay? So let's just evaluate this. We let u equals t squared plus 1, du equals 2t dt. Okay? If t equals 0, u equals 1. If t equals 1, u equals 2. So for this guy, we have the integral from 1 up to 2, square root of u du over 2. Don't forget that over 2. So it came from this part here. So which means we'll just have 1 half u raised to 3 halves over 2 evaluated u equals 1 up to u equals 2. So this is equal to, you have 1/4 times u, or 2 raised to 3 halves minus 1. So this will be, you can write the final answer in this form. Okay? Questions? Next, find the arc length of the curve x equals cosine 2t, y equals sine 2t from t equals 0 to t equals pi over 2. Okay? T equals 0 to t equals pi over 2. Fun fact, this guy here, so this guy here on the given interval, this is just a circle. Okay? This is just a circle. It is of radius 1. So of radius 1. So if we are going to find the arc length, we should get what? 2 pi r. So we are expecting 2 pi. Okay, we are expecting 2 pi. Let us see. Dx over dt. So derivative of cosine 2t with respect to t, that's negative 2 sine 2t. And then dy over dt, derivative of sine 2t with respect to t, that's 2 cosine 2t. Okay? And this guy here, they will not be 0 at the same time. Okay? So dx over dt equals 0 when t equals pi over 4, and also, oh no, it's not t equals pi over 4. T equals pi over 2 and 0. Whereas dy over dt, this is equal to 0 when you have t equals pi over 4. So they will not be 0 at the same time. Okay? This guy means curve is smooth on the interval 0 up to pi over 2. Okay? So we have arc length. This is the integral from 0 to pi over 2. We have the square root. Let me write the square thing in this part. We have minus 2 cosine 2t squared plus 2 sine 2t squared dt. This is equal to integral from 0 up to pi over 2 square root of, we can factor out 4. So we'll have 4 and then cosine squared 2t plus sine squared 2t. Okay? And then we will have the dt. This guy here, this is just equal to 1. Okay? So, what will happen? What will happen in here? This guy will just have integral from 0 up to pi over 2 of 2 dt. So, if we continue, this will be equal to 2 times pi over 2. And this is equal to pi. So, is this a circle? It should be semicircle. circle or semicircle? Uh, so based on this, our L, it's just pi, and I said this is of radius equal to 1. So I am expecting 2 pi if this is the full circle. Maybe this is just a semicircle. Okay, maybe this is just a semicircle. But anyway, based on this computation, unless I missed something, based on this computation, we got the arc length equals pi. And that's the arc length of a semicircle. Okay? So again, this is just a semicircle. So let me write it here. Anyway, show that the total arc length of the ellipse x equals 2 cosine t, y equals sine t, where t is between 0 to 2 pi. This is given by this formula in here. So this formula in here. So yeah, based on this and according to this total arc length of an ellipse, so the interval is from 0 to 2 pi. So this guy here, it's a semicircle. So I have to correct what I said from earlier. Okay. So let us calculate this formula here. We have, all we need to do is, well, to get dx over dt, um, it's just negative 2 sine t dy over dt. This is equal to cosine t. Okay? And they will not be 0 at the same time. So in here, dx over dt, this is equal to 0 when t equals 0, pi, and 2 pi. On the other hand, dy over dt, this is equal to 0 when t equals pi over 2 and 3 pi over 2, which means that curve is smooth. Okay, so from here, what do we have? So dx over dt squared, well, this is just for sine squared t, dy over dt, quantity squared. This is just cosine squared t. This means that you have dx over dt squared plus dy over dt squared. This is what? 4 sine squared t plus cosine squared t. But this is just what? 3 sine squared t plus quantity sine squared t plus cosine squared t. And again, this is just equal to 1. Okay? And now, this is an ellipse. Okay? This guy here, it's an ellipse. If we try to sketch the ellipse, so this is 2 here, this is negative 2, This is 1. This is 1 here. The ellipse will be something like this. Okay? Now, from this point up to this point here, that's the interval t from 0 to pi over 2. And then from this point up to this point here, the interval for t will be from pi over 2 up to pi. Okay? And then from this point up to this point here, you have the interval for t. This is from pi up to 3 pi over 2. And from this point up to this point, the interval for t is from 3 pi over 2 up to 2 pi. So that's the full ellipse. But this is an ellipse. This is symmetric with respect to the origin. So it's enough. It's enough to get the arc length on this part. Okay? It's enough to get the arc length on this part and then multiply it by 4. Okay? So the total arc length is, you have the integral, and I said multiply it to 4, but we'll just integrate from 0 up to pi over 2. And then you have square root of dx over dt squared plus dy over dt squared, and then you have the dt there. But dx over dt squared, it's given by this guy here. And that's the formula we are looking for. We have the integral from 0 up to pi over 2 square root of 1 plus 3 sine squared t, and then the dt.